In this video, we're going to take a look at arc length and surface area. We're going to use integration to find each of these things. So think about finding the length of a straight line. Eventually, we're going to use the idea of finding the length of a straight line to approximate finding the length of a curve. So if I think about a straight line, we have a distance formula here that is the distance is equal to a squared, the square root of a squared plus b squared. That comes from the Pythagorean theorem. As you go from one point to another point, we have change in y and change in x, or change in x and change in y as our a and b. And then c is the length of that line. In other words, let's say I want to calculate the distance from the point 23 to the point 61. So I want to calculate the distance of this line here that connects those 2 points. Well, I can draw a right triangle. The right triangle has legs, one of which goes from 3 down to 1, and the other which goes from an x value of 2 to an x value of 6. So a y value of 3 down to a y value of 1. The other leg goes from the x value of 2 to the x value of 6. The A and the B will, depending on which leg I call length A and which one I call length B, will be the change in y and the change in x. So we get the Pythagorean theorem because of this, and the distance formula pops out of there. So if we are dealing with a straight line, then we can just use the distance formula or the Pythagorean theorem to find the distance of that straight line from one point to another. However, if our curve is not straight, what I'm going to end up doing is I'm going to end up approximating with straight pieces. So I cut it up into a lot of little sections and I approximate the length with a straight piece. And then I'm going to sum up those straight pieces. That sum will give me a good approximate answer if I have enough little pieces. And just like we always do, in order to create a perfect match, we take the limit as I get more and more and more pieces, and that'll give me the arc length, or the length of that smooth curve. When we take the limits, remember the distance is the square root of a squared plus b squared. The a squared could be change in x squared, so we can write that as change in x squared. The b squared could be change in y squared. You can actually factor out a change in x. If I factor out a change in x squared underneath this square root symbol, then I end up with this. I can take the square root of the change in x squared, and then the square root of 1 plus change in y squared over change in x squared separately. And when I take the limit as that the pieces get smaller and smaller and smaller, that change in x will become a differential with respect to x. And I'll end up with this as the distance of one of those little pieces. Notice this is the square root of 1 plus the derivative of y with respect to x squared times my differential dx. And that's what the arc length formula becomes. If we utilize x values, the arc length formula is an integration of the square root of 1 plus the derivative of f squared integrated with respect to x. Now you can solve for y. You could have x as a function of y, and so we can use g of y as our function there. If we do that, then everything stays the same except for we're using y bounds now. So traditionally we'll start with c and end at d. And then we have the square root of 1 plus the derivative of g with respect squared integrated with respect to y. Be careful here. Again, this is the derivative, and then we're squaring the entire derivative and then adding 1 out front. So make sure we have the square. We'll have to make sure that we have the squaring in the correct place, and we'll have to make sure that we have the correct derivative. But that's it. That's the basic idea of how the arc length is obtained. So basically, imagine I want to find the arc length from the point 0, 1 to the point 3, 4 on this curve. So that's the same as asking if I laid out a string on top of this curve and that string started at the point 0, 1 and ended at the point 3, 4. So started at 0, 1, ended at 3, 4. How long would the string be if I stretched it out and measured it? So that's what we're saying about arc length. One way you can do that is, oh, no, I want to start at 0. Yeah. So one way I can do that is just view this section of the curve. And what we're going to do is we're going to split this up into lots of little pieces. Now, obviously, I can't do that too many times, but now I've, made a point, and each of my points have been basically a half of a unit away from each other in terms of their x values. So I started at 0, and then a half, and then 1, and then 1.5, and then 2, and 3. And if I draw a bunch of straight lines that connect these 2 points, back-to-back points, and then add up the lengths of each of those straight lines, I'll get a pretty good approximation of the length of the curve. And then if I take more and more points, if I don't just jump by 0.5, but if I jump instead by, 0.1, then it's going to be even a better approximation. And I just keep doing that over and over, taking that limit. And as the x value change goes to 0, so as I get smaller and smaller jumps in terms of x values between my points, taking the limit as x value goes to 0 is going to give me the actual arc length of my original curve. Again, from this point of 0, 1 to this point of 3, 4. So let's calculate what the actual arc length is of that parabola pointed down from x value of 0 to x value of 3. So we have y equals negative x squared plus 4x plus 1. and we want to find the arc length of that curve from x equals 0 to x equals 3. Now, in this case, we can see that y is set up as a function of x. So we're getting y equals a function of x. And therefore, I'm going to set up my arc length having integrated with respect to x, because then I don't have to try to solve for x. So the f prime here is just the curve I'm talking about, again, if y is written as a function of x. So the first thing I need to do is realize that the f of x that we're talking about is negative x squared plus 4x plus 1. And therefore, the derivative of f of x is equal to negative 2x plus 4. We know our bounds are going from x value of 0 to x value of 3. So from 0 up to 3. And now I see that my derivative is negative 2x plus 4. So I put that expression in for the derivative. Be careful that we have all of the correct squaring and all of that. You can probably do this by hand if you'd like, but it's much more efficient if we just utilize the calculator. So that's what I am going to do. I'm going to integrate from 0 to 3 the square root of 1 plus the quantity negative 2x plus 4. Again, that quantity being squared. And I'm going to integrate with respect to x. Make sure that you put parentheses around this inside negative 2x plus 4 because that entire thing is being squared. When I got my answer came out to close to 6.13. Again, if you wanted to try to do it by hand, it's a fairly complicated integration because you're dealing with the square root and you have squareds underneath. It's doable with some high-level techniques, but in this case, it's easier to just get the approximation of about 6.13. So that's how we calculate arc length. Arc length of that curve from 0 to 3 gives us about 6.13. Again, that means if I take that curve, this is the one I drawn in my visualization. If I take that curve, if I were to put a string on top of that, the length of the string would be about 6.13. Or in other words, if you held this point and somebody else held this point, stretched it out, the length of that, of walking along this line or walking along this curve would be about 6.13. So if somebody walked here and you were tracking their position, or an ant were walking along this curve, they would have walked about 6.13 units. So that's the idea of arc length. Let's try another example. I want you to find the arc length of the curve y equals sine of x on the interval 0 to pi. So we're finding the length of the sine curve from 0 to pi. If you want to do this on your own, push pause on the video. Otherwise, I will do it just a couple of seconds. In this case, we have y equals sine of x. So we have y is written as a function of x. The closed interval from 0 to pi is referring to x value of 0 and x value of pi as our starting and stopping place. So we're going to be integrating with respect to x because I have y is written as a function of x. Specifically, this y is my f of x. Now, I need to take the derivative. Sometimes, just for the sake of speed, I don't rewrite it as f of x. I just write y equals sine of x, and then I write y prime as the derivative. The derivative of sine, obviously, is cosine. And now I'm ready to set up my integration. The derivative of my function is cosine of x. I'm going to square that, then add 1, then take the square root, and integrate that from 0 to pi. You could try to do this by hand if you'd like, but it's a lot easier to deal with this using your calculator. So that's what I'm going to do. I'm going to type that into my calculator. Now, if you are using your calculator, we're doing calculus with trig functions. So make sure you're in radian mode in your calculator. The derivative of sine is cosine if you're in radian mode. If you're in degrees, then that is not the case. So if you're using radians, then all of our derivatives that we know work out nicely. If we were using degrees, our derivatives would not be the same thing. So make sure you're in, that's a lengthy talk just to say, make sure you're in radian mode. So when we integrate that, I ended up with a 3.82 roughly. I shouldn't say equals. That's the approximate answer, is about 3.82 is the arc length of sine on the interval from 0 to pi. Now the graph of the sine curve looks like this. Looks like that, wave there. From 0 to pi means we're looking at the section between this point and this point. So the single hump here that's above the x-axis. We can highlight that if we want. So that, the length of that curve is roughly 3.82. That's what we're saying. In the first two examples, we had y written as a function of x. Here in this third example, we have x is equal to a function of y, and we're given y value bounds. It says go from y of -3 to a y of +3. If we have this situation, that's perfectly fine. We're just going to use the arc length formula. If we have y bounds, we can use the arc length formula that's done with respect to y. And g of y is, we're going to have x as a function of y. So we can use that. We could have also tried to solve for y and then use the x bounds too. with this arc length formula, but in that case, we have to break it up in example 3. So we're just going to use the y values directly and utilize this second arc length formula. So again, first two, we saw y as a function of x. This third one, we have x as a function of y. Should be fairly straightforward. Since x is a function of y, we're going to say g of y, my function of y, is equal to y squared. If I take the derivative of that function, I'm taking the derivative with respect to y, I end up getting 2y. So my arc length is going to become, we're going to integrate from -3 up to +3. And I'm going to integrate I'm going to integrate the square root of 1 plus quantity 2y squared with respect to y. Again, I'm just going to utilize my calculator to do that. Hopefully we know how to integrate. Shouldn't be too crazy to integrate this definite integral with respect to y. Again, you can use the variable key if you'd like and use any letter you want when you're integrating. I end up with about 19.49. So about 19.49 as the arc length of that curve from y of -3 to a y of +3. Let's take a look at the drawing of that curve. Obviously, we're going to get a parabola. It's going to be pointing to the right. So pretty standard curve to deal with, but we'll just take a look at it and look and decide if that 19.49 makes sense. The graph of this parabola, like I said, it's a parabola pointing right. The vertex is at the origin. Notice that if we measure the length here, going from 9, well, let's start at the bottom, from 9 -3, so y value of -3, all the way up to 0, we definitely have to go 9 plus a little bit extra. And then from 0 to 9 in the x value, so from the origin to 9, 3, again, we know that length is going to be more than 9 just because we can see it stretched out in the x direction 9, and then it's stretched out in the y direction 3. So it's going to be whatever this distance is doubled. And it does, again, kind of 19.49 looks like it makes sense. Again, as a point travels along this curve, that point will have traveled 19.49 units, approximately. So there we go. That's the idea of arc length, where now our function is x is a function of y. The fourth example says, well, what if we have neither? What if our function is not written as y is a function of x and not written as x is a function of y? But what if we have some sort of equation that relates x and y, we can graph this equation, and we want to find the arc length, let's say from x equals 0 to x equals 8. Now, sometimes we have to be pretty careful about how we solve this, and because obviously we have an x squared in here, so if there are negative x's, then the negative, let's say -2 for x would give you the same thing as +2 for x. So if you're solving for x and take the square root of both sides, you have to worry about negative square root versus positive square root. But if all of our x's are positive, then if we take a square root of both sides, we know we can take the positive square root of the left-hand side if I'm solving for x. If I'm solving for y, I'm going to have to do a cube root on the left and right-hand side. And that's fine as well, because cube roots, there's no problem with doing a cube root of any number, any real number. So this equation can be solved either for x or for y. And therefore, I can use either the arc length formula for x, or when I'm integrating with respect to x, or the arc length formula when I'm integrating with respect to y. Either way is perfectly fine. I'll do both ways. Let's start out, since I have x bounds, x equals 0 to x equals 8, it's probably a little bit more natural to do your integration with respect to x. Again, I'll do it both ways, but probably a little bit more natural to integrate with respect to x because our x bounds are given. But we'll do the other way as well. So let's start with integration with respect to x. That means I need to solve this equation for y. I need to end up with y equals something. So again, I'm just manipulating now, and I could take the cube root of both sides, or I could think of this as taking both sides to the 1/3 power. So I'm going to take x squared and raise that to the 1/3 power, which, by the way, is x to the 2/3 on the right-hand side. When I add 1 to both sides, that's what I get. I get y equals x to the 2/3 power plus 1. So that's my y function, which again is basically my f of x in this formula. If I take the derivative of that, I'll just call it y prime, I get 2/3 x to the, when I subtract 1, I get -1/3. So x to the -1/3 power, the plus 1 has a derivative of 0. So now I have my derivative of my f of x. To find the arc length, oops, now I can just plug that in. I always like copy and paste. It's always a nice thing. My x values, it said, were ranging from 0 to 8. My derivative now I know as 2/3 x to the 1/3 power. And so this is the integration that I get. We are going to integrate the square root of 1 plus quantity 2/3 x to the negative 1/3. I mistyped that. X to the negative 1/3 squared. And we're integrating that from 0 to 8. This, again, is something that I'm going to plug into my calculator and get an approximate value for. And when I do that, hopefully I type it in correctly. Make sure that, because we have lots of exponents, make sure that the squared is around the 2/3 x to the negative 1/3 power. It'll probably take a second for your calculator to come up with the answer or with an approximate answer, but your calculator will come up with an approximate answer. I got about 9.07. Okay. The reason why your calculator took so long to come up with that approximate answer is because we are dealing with x to a negative power and it's underneath a square root, and with zeros, with negative powers, sometimes that can be tough to calculate. So we end up getting about 9.07. And again, all we had to do was solve for y and then take a derivative of that y. Then plug it into our arc length formula with the proper x bounds. Let's do it the other way now. Let's say, what if I wanted to actually solve for x? I've already written that part down here. So we want to solve for x, and we want to integrate with respect to y. Now in this case, we have y minus 1 cubed equals x squared. I'll write it in this way. Because I'm dealing with positive x values, the x values are going from 0 to 8. When I take a square root, I'm okay to take a positive square root. And a positive square root is the same thing as a 1/2 power. So I am going to call this the quantity y minus 1 raised to 3 to the 1/2 power, which is 3/2 as the exponent. That means if I want to take the derivative with respect to y, I'm going to end up with 3/2 times y minus 1. When I subtract 1 from the exponent, I get a 1/2. And then I'd multiply by the derivative of the inside function, which is just 1, which doesn't change anything. So this is the derivative when I write my function with respect to y. I have to be very careful about the bounds. Here I'm given x value bounds. X goes from 0 to 8. Well, if x goes from 0 to 8, what does y go to? It's probably easiest to use this equation in order to figure out what the y bounds are instead of my original equation. If I plug in 0 for x, I'll get a y value of 1. If I plug in 8, well, 8 to the 2/3 plus 1. becomes a 5. So 8 to the 2/3 is a 4, plus 1 becomes a 5. So we're going from y equals 1 to y equals 5. You could have also solved that by plugging in 0 into this equation and then solving for y, and then plugging 8 into this equation for x and solving for y. So y bounds are going to go from 0, x bounds go from 0 to 8, whereas the y value bounds are going from 1 to 5. Now we're ready to set up our arc length. The bounds are going to go from 1 to 5, square root of 1 plus the derivative squared. The derivative is 3/2 y minus 1 raised to the 1/2 power. When you square that, you get some nice things. I won't go through all of the details, but you can simplify that if you're doing this by hand. And it's kind of a nice simplification because squaring a 1/2 just gives you a y minus 1, and then we're squaring the 3/2 as well. Squaring something to a 1/2 power gets rid of it. Squaring 3/2 gives you 9/4. Doesn't matter though, whichever way you prefer to type it in. If you want to do a little bit of simplification, you can. If you don't want to do simplification, then you don't have to. You can just type it in as is. Either way, when you type it in, this calculation goes a lot quicker. Your calculator does this a lot faster. You get the same answer, or at least roughly the same answer. If you go out more decimal places, they are actually rounded differently because of, again, the algorithm. But 9.07, and your calculator should calculate this one a lot faster because there's no sort of bad spots. We're plugging in 0, or we're plugging in 1. We don't have any negative exponents, and so on and so forth. So this was a little bit easier for the calculator to handle, but we had to find the y values. This one was a little bit tougher for the calculator to handle, but we were given the x values. And so either way, we get 9.07, whether we integrate with respect to x or integrate with respect to y. It's just a matter of preference of which path you choose. Just for the sake of saying that we've seen it, by the way, this x squared equals y minus 1 cubed, or y minus 1 cubed equals x squared, it actually looks like this. It looks like this curve kind of has a point at 0, 1. Some people, when they're kids and they draw birds in the sky real quick, they make them look a little bit like that. But it has a point at 0, 1, sharp point at 0, 1. And then obviously we saw it goes out to the 0.85. So we're saying that section of the curve from 0, 1 to 8.5 has length, which is about 9.07. If you walk along it. So there we go. That's the idea of arc length. And we can see that in this case, we could use either the arc length formula for integrating with respect to y, or the arc length formula for integrating with respect to x, there are some equations where you'll have to use one or the other. In fact, if you were going to try to integrate with respect to y on this equation in example 1, that would have been very, very difficult. We wouldn't have been able to do it. But with respect to x, it wasn't an issue. So it is important that we sort of have both options. Again, because there are some equations where only integration with respect to x is really going to work. There are other equations where integration with respect to y is the only one that could work. This example 3, we could have sort of hacked it and figured out a way to do it. But there are certain equations where integration with respect to y is the only option. Here, integration with respect to y was the best option. And then there are certain cases where you can integrate with respect to y or integrate with respect to x. And either option is perfectly fine. This section covers arc length, but it also covers the idea of surface area too. So we're going to take that arc length formula that we just used, and we're going to apply some of those details that we saw in arc length to the concept of surface area. Now, what kind of surface area are we talking about? We're talking about the surface area when we revolve a curve around a horizontal line or a vertical line. Kind of like the revolution we were doing when we found value. So we take a curve in space and we're going to revolve it around either a horizontal line or a vertical line, like we did when we found value. So let's take a look at how this works. I have graphed y equals x squared in the xy plane here. Let's say we take a section of that curve. Let's say the section goes from 0 up to 2. So x equals 0 to x equals 2. And we want to take that section, this piece of the curve, and rotate it around, let's say, the x-axis. If I do that, what's going to happen is I'm going to get a figure which is sort of just the outside edge of one of those volume figures that I was talking about, or that we discussed in the previous couple of sections. So I get this figure, which kind of, in this case, if I turn it the right way, looks like a funnel shape, curved funnel shape. Now, when we look at this, we're going to find the surface area. And because this has essentially no width, the curve has no width, the surface area on one side is going to be the same as the surface area on the other. And so those two surface areas will be equal, and we're going to be finding that. We're not going to be finding both the inside and the outside surface area. We're just going to be finding one of those surface areas. So that's the idea. We take a curve, we revolve it around a horizontal line. Now this time I revolved it around the x-axis. You could obviously revolve it around the y-axis as well. You could revolve it around the line y equals -2 or x equals -4. Lots of different ways we can revolve that. But That's what's going on. When we do this, what we're going to do in order to actually find the surface area is we're going to take little chunks of my y equals x squared, little chunk pieces, and we're going to take those line sections that we had before. Let me actually change this to a different color. That didn't work very well. I thought it'd show up better with a different color, but we're taking these little line segments and we take lots of them and we revolve each line segment around the x-axis. This makes sort of what I would refer to as a ribbon shape. And so that ribbon shape is going to be a part of my three-dimensional figure, or at least an approximation for that three-dimensional figure, at least a piece of that three-dimensional figure. And if I sum them all up, I get a pretty good approximation. If I find the area of each ribbon, so find the area of each of these little ribbons. Then sum them all up, you get an approximation for surface area, and then do our standard thing where we make the ribbons thinner and thinner and thinner and thinner. So I have a bunch of ribbons doing an approximation for the surface area of this three-dimensional object that I get by revolving, in this case, y equals x squared around the x-axis. Hopefully that makes sense. We're approximating with a bunch of ribbons. Notice that the angle that this ribbon is cut on follows the angle of my curve, which would be the slope of the tangent line of my curve. And so when I am looking at this, those little sections will be approximated by slope of tangent lines, and I'll get an arc length formula embedded into my surface area. I'm basically going to get the arc length piece and then rotating it around a big circle of some radius. So because this ribbon is angled, we'll see an arc length piece and then times circle. And again, when I rotate it around, I'm measuring the circumference of the circle, which is 2 times pi times some radius. So I'm going to end up with 2 times pi some times a radius times an arc length formula. This slide says what I was just showing. We're going to cut those little bitty sections of our arc length, and then we're going to revolve around some circle, and that'll create some ribbons. The circumference of any circle is 2 times pi times the radius, and each ribbon surface will be approximately that circumference times arc length. When I add those up, if I use x values, then I'm going to have a surface area, which is 2 times pi, integrate from a to b, a radius times the arc length calculation of square root of 1 plus derivative of f squared, all integrated with respect to x. And if I'm going to use y values, then I do the exact same thing, but using y values. I get surface area as 2 pi, integrate from c to d, my radius with respect to y, times the square root of 1 plus the derivative of g squared, all integrated with respect to y. So I get these two surface area formulas. One, if I want to use x values. A second, if I want to use y values. Notice that we are not saying that if you rotate around a horizontal line, you have to use x values. Or if you rotate around a vertical line, you have to use y values. In fact, we don't have to do that. And we'll see that in a couple of examples. So if I want to use x values, I can sometimes use x values when I rotate around a horizontal line, and I can also sometimes use x values when I rotate around a vertical line. The same thing with y values. I can use y values when I go horizontal line or vertical line rotation. Again, sometimes, depending on how my formulas work out. Let's do an example where we find the surface area formed by revolving y equals negative x squared plus 4x plus 1 around the x-axis on the closed interval from 0 to 3. So that means from x equals 0 to x equals 3. We saw this curve before from 0 to 3, and we found the arc length of that curve earlier. So now we're going to find the surface area we get when we revolve that piece around the x-axis. Before we get too far into this, I'm going to draw a picture and I'm going to think through what revolving around the x-axis is going to look like. So the x-axis is the line y equals 0, obviously right there. And if we're looking at this curve I'm describing from 0 to 3, I get this section, and I'm going to revolve it around the x-axis. So that section revolved around the x-axis. The derivative that we use inside the arc length portion is going to be the derivative of the function itself. The bounds are pretty obvious. They go from 0 to 3 as far as the x values go. So I'm going to integrate with respect to x values. In terms of the radius, that's the interesting part. So if I take a point on this curve and I draw the radius, well, the radius of my circle is going to go from the curve down to this line that I'm rotating it around. So from the curve down to the line I'm rotating it around will be my radius. I'm rotating it around the line, y equals 0, that is the x-axis. So that's how I set up my surface area. Let's do the algebra now. Now, it doesn't matter the order of what I do things or how I say things. It matters how I put them in, obviously. But the first thing I'm going to say is we're going to integrate. Since we're integrating with respect to x, our x values are going to go from 0 to 3. I'll put those in first. So we're going to integrate from 0 to 3. Let me do the derivative, the f prime, next. The f prime is the same as we had the first time we did this. That's the derivative of my original function. That's negative 2x plus 4. So I'm putting negative 2x plus 4 inside the square root. Underneath, we have 1 plus derivative squared. The radius is the key part. The radius, like we said, goes from the curve down to the x-axis, down to the line y equals 0. So we're going to go from negative x squared plus 4x plus 1 down to the curve y equals 0. Now, the reason I'm writing it this way is because I'm integrating with respect to x. Since I'm integrating with respect to x, my curve is going to be the expression, since that's using the variable x. Obviously, if I don't want to write the minus 0, I don't have to. The one thing you do have to do, though, is make sure that this radius is all in parentheses before you multiply by the square root. Because if it's not, if you don't write it in parentheses, then the square root will only be multiplied by the last number in this expression. So it would only be multiplied by 1 if you forgot the parentheses. You want the entire radius to be multiplied times the entire square root. At this point, you can integrate, I usually anyways, plug it into my calculator. Don't forget that there is a 2 pi out front. It is, in this case, a lot to plug in, but remember the radius is original function height down to y equals 0, and this part uses the derivative. So this part is using the original function, this part is using the derivative. Again, it takes me a second to type this in, but once I do, then my calculator does all of the difficult work. Again, sometimes you have to be really careful about how you type it in, getting all of the parentheses correct, making sure that your bounds are correct. If I do type it in, what I get is approximately 135.41. That's a little over 43.1 pi. So that's what I end up with. Doing this by hand would take quite a bit of time. So there we go. That's the idea. So surface area is 2 pi radius times the square root of 1 plus the derivative of f squared, integrated with respect to x, and then we're off to the races. Now on this example, it'd be very, very hard to rewrite this as x is equal to a function of y, so I would not want to integrate with respect to y. I wouldn't have an option really of doing that because it's really, really hard to solve this for x, solve that original equation for x. So we're kind of forced to integrate with respect to x in this case. So, by the way, the object that we're creating in 3 dimensions um, is this curve rotated around the x-axis. And if we do that, we get this kind of, I don't know, looks like a piece of pottery almost, has a hole in the middle, almost looks like a bowl-shaped thing with a hole at the bottom. So that's what we have created, and we're saying the surface area of that is about 135.41 surface area of this object here. Again, hard to see, but that's what it is. So it's an interesting shape is all we're getting at. It's an interesting 3-dimensional shape. And obviously it doesn't have any value because the edge of it really doesn't have any width. So we don't have any value, but we do have a surface area of that object. The natural follow-up to example 5 is to say, what if we, instead of revolved it around the x-axis, what if we revolved that object around another line? Like, let's say the line y equals -5. So we're going to take y equals -x² plus 4x plus 1 again. We're going to use the interval from 0 to 3. And we are going to revolve that section of curve around the line y equals -5. Since the curve has no thickness or no width or no, yeah, I like to say thickness. So since the curve has no thickness, it won't make sense talking about a value, but it will make sense talking about a surface area. So the surface area is what we're looking for. So same graph that we had earlier in 2 dimensions, but now I'm going to rotate around y equals -5. And if you think about, as always, just taking any spot on here, radius is going to go all the way from that top of the curve that I'm looking at all the way down to the line I'm rotating it around. Instead of rotating it around the x-axis, I'm rotating it around y equals -5. So that's what my radius is doing. By the way, this curve is above -5 always, and therefore we're going to do curve minus -5 as my radius. In this case, we can use all of the stuff we did in the previous problem because we're using the same, not all of the stuff, but most of the stuff we used in the previous problem because we're using the same length of arc length. So same curve, same interval. But now instead of y equals 0, we're going from y equals -5. So now my radius goes from the curve down to -5. So I'm going to get -x² plus 4x plus 1 minus a -5. If you want to combine these, when you combine them, all you have to do is say +1 plus 5 is going to add to a 6. But when you type it in, just make sure that this entire thing is inside of parentheses and that entire expression is multiplied times the square root. So derivative there is still -2x plus 4. We're just using a different radius. When it's all said and done, I got an approximate surface area of 327.86. Again, that's just from typing this in to my calculator. Notice that was a much bigger surface area than the previous problem. The previous problem had a surface area of 135.41. This has a surface area of 327.86. That's because increasing the radius gives me a much longer circle to deal with. And that gives me a lot more surface area of the object that I've created. In this case, again, if I look at a picture, I'm going to have this curve rotated all the way around the y equals -5. When I do that, I get this shape of an object. When I had y equals 0 as my line that I was rotating around, whoops, I got a much more compact object. The edge of it has the same curve as arc length as this bigger one, but obviously the bigger one is going around a much bigger circle, so it's going to end up with a much bigger surface area. So that's why we're ending up with, again, a much bigger surface area when we rotate around the line y equals -5. Get that sort of object. Let's do another example. Let's find the surface area formed by revolving a different curve, that is y equals x squared plus 2, around the y-axis. I'm going to show you how to, on the interval from 0 to 2. So x goes from 0 to 2. We're going to revolve around the y-axis. I'm going to show you a couple of different ways to do this. Now, in the previous two examples, we've always rotated around horizontal lines. So we use the surface area formula where we've integrated with respect to x. And you might get the impression that horizontal lines always we have to integrate with respect to x. It turns out that is not the case. I'll show you how to do both ways using integration with respect to x and using integration with respect to y for this example 7. So we want to rotate around the y-axis on the interval from x equals 0 to x equals 2. Y equals x squared plus 2 is this parabola. We're going from 0, x equals 0, to x equals 2, and we're going to revolve that around the y-axis, so the line x equals 0. If I'm looking at this section of the curve that I'm going to revolve, it goes from the point 0, the point 02 all the way to the point 26. Okay, let me just focus on that little section of my parabola. This is what I'm going to be revolving around the y-axis. In this case, what we can see is that the radius is going to go from the curve is going to have positive x values, all the way down to x equals 0. So that's what the radius is doing, from the curve down to x equals 0. And if I want to, I could say, let's integrate with respect to y. If I'm integrating with respect to y is going from a value of 2 out to a value of 6. The radius goes from the curve down to x equals 0. If I write my curve as x equals a function of y, then I can do essentially the same thing I did in the previous two examples. So that's what we'll do first. We'll integrate and find the surface area by integrating with respect to y. Now let us not forget that this closed interval is not referring to y values, it's referring to x values. So the y values are going from 2 to 6. So just so that we have that. Oh. If I want to integrate with respect to y, then I need to create a function where x is equal to an expression in y. We get y equals x squared plus 2. Let's solve that for x. Subtract 2 from both sides, I get x squared on one side, and then the other side would be y minus 2. Because we're in the first quadrant, I know my x values are going to be positive, so x can be the positive square root of y minus 2. I know I'm going to take a derivative, so I'm going to write that as y minus 2 to the 0.5 power. That's the same as the square root of y minus 2. So this is my x, which is the same thing as the g of y, my function g of y. If I take a derivative with respect to y, I end up with 0.5 times the quantity y minus 2 raised to the negative 0.5 power. And then derivative of the inside function is 1. 1 times anything doesn't change anything. So this is my derivative. This is my x, which is my g of y function. This x prime is my g prime of y function. So that's what I'm going to be plugging in here. I know y values are going to range from 2 to 6. And we said the radius goes from my function down to the x equals 0 line, which is the y-axis. So the y-axis, again, is the line x equals 0. So we're going from my function down to 0. Now I'm all set up. Now I can take this general formula and plug in the specifics of this situation. We're going from a y of 2 to a y of 6. We said the radius goes from my function of y minus 2 raised to the 0.5 power down to x equals 0. And we said the derivative of g is 0.5 times the quantity y minus 2 raised to the negative 0.5 power. I put that all into my surface area formula. Once again, if you'd like to try to do this by hand, you could. I tend not to like to try to do this by hand. I would rather get an approximate answer by plugging it into my calculator. That's what I'm going to end up doing. Again, if we're plugging things into our calculator and calculating with respect to y, really is not going to change much as far as how I plug things in. So y minus 2 raised to the 0.5 power all multiplied times the square root of 1 plus 0.5 times y minus 2 raised to the negative 0.5 power squared. And then you hope you plug it in right. There's lots of parentheses to deal with, and there's lots of issues to watch out for. But if you plug it in right, I think you end up with about 36.18. So if I wanted to integrate with respect to y, I just have to create a function where g of y or x is equal to a function of y, take the derivative of that, and then my radius goes from my function down to x equals 0, and I have to use y bounds. Now, like I've been saying explicitly, just because we were revolving around a vertical line does not mean I have to find the surface area by integrating with respect to y. I actually could have also integrated with respect to x. The big insight that allows me to integrate with respect to x is to realize that if I draw my radius this way, and I'm integrating with respect to x, then this right-hand side is simply an arbitrary x value somewhere between 0 and 2. And the left-hand side is always 0 in terms of what x is, because that's the vertical line, x equals 0. So the right-hand side of this, if I'm integrating with respect to x, is just some arbitrary x value, kind of like the shell method radius. So with the shell method radius of finding volume, we went from an arbitrary x value down to the line we're rotating around. Well, if I'm integrating with respect to x, that can be my radius here as well. So I don't want to use y's, I want to use x's. Let's use x's there. My surface area, if I want to integrate with respect to x, that formula becomes, since x's range from 0 to 2, my a is going to be 0, my b is going to be 2. And here's the insight. The radius is now from an arbitrary x between 0 and 2 down to the x equals 0. So the radius is simply just x minus 0. The derivative of f is just the derivative of this. So I'm going to call that y prime. That is just 2x. Notice that this is a much, much easier integration to deal with than the previous example was, the previous way to solve this was. In fact, if you really want to, you can do this by hand if you want. This one is doable by hand. The previous one was not really doable by hand. I'm still not going to do it by hand because it's not worth my time, but you could. That's my point. When it's all said and done, you get approximately 36.18 using this method as well. What made this so much easier is that the derivative and the function itself were really easy to deal with in y equals a function of x form. They were much harder to deal with if I have x is equal to a function of y form. That was a lot more difficult to deal with. And then the radius is a little bit more complex as well, because if I'm integrating with respect to y, then my radius has to be in terms of y values minus 0. Whereas if I integrated with respect to x, my radius is just arbitrary x value minus 0. So obviously this one, it was much easier to integrate with respect to x. And as usual, I want to just say, if we want to be on the same page, the object we got when we did that looks like a cup. A little bit of a cup there, revolved around the x-axis. No holes in this cup. So that's what we're getting, this sort of object. You probably could visualize that already, but I wanted to at least draw it in 3 dimensions once. So that cup has surface area of about 36.18, and we found that in 2 different ways. Now, obviously, in general, what we're going to do in any time we can define the surface area, integrating with respect to x or integrating with respect to y, we're going to use the easiest option. You don't need to use both options every time. That's kind of a waste of time and energy and effort. It's a much better strategy to use the easiest option. So this was a really nice function with respect to x. So I'd probably have used integration with respect to x as opposed to integration with respect to y. If I had a nice function where x was a function of y, I would probably use integration with respect to y. But again, in general, if you can do it 2 ways, use the easier option. Let's do this now. Let's take the same function and rotate it around the line y equals 0. The line y equals 0 is the x-axis, and again, on the interval from 0 to 2. If you want to try this on your own, push pause, try it on your own. I'll give a couple of seconds and then I will do the problem. All right, so we don't have to draw anything new. We have our section of curve. Now we rotate it around the x-axis, so the line y equals 0. And the radius is going to be from the curve down to the x-axis. If I'm going to use integration with respect to x because this is just an easier function to deal with when I'm integrating with respect to x. Easier to take derivatives of, easier to mess with. So if I'm dealing with respect to x, this curve has expression x squared plus 2. So we're going to go from x squared plus 2 down to 0. That's where my radius is going to be. I've already taken the derivative from the last example, so derivative of y with respect to x is 2x. That means my surface area can be found by integrating from 0 to 2 in my x bounds. Like I said, my radius goes from the curve down to y equals 0. So y equals x squared plus 2 down to y equals 0. So basically my radius is going to be x squared plus 2. The derivative of my function is 2x. Again, this is pretty straightforward to integrate. Just you got to make sure that whenever you're inputting things, you put parentheses around the correct things. All right. So I'm plugging that into my calculator as we speak. I haven't pre-plugged that in. I should have probably, but when I did my integration and I typed this all in, I ended up with approximately 111.62. Obviously, the surface area of the object we get revolving around the x-axis is much different than the surface area that we got revolving around the y-axis because these are very different shaped figures. But that's it. That's the whole thing. If you wanted to solve for y and try to find a radius with respect to y, you could. It's not impossible. In fact, we could have used some things that we already did use. So I will do that in this case. The radius would have went from a y value, arbitrary y value, down to 0. The integration with respect to y would have gone from 2 to 6. Remember, that was my integration with respect to y here. So my radius would have been y minus 0. And then when I take the derivative inside of the arc length piece, that would have been 0.5 times y minus 2 to the negative 0.5 power. and we would have ended up with that integration. That integration is a little bit harder to plug in, but it's perfectly fine to plug in. It's not a problem. It will take quite a bit longer for your calculator to calculate this, but at the end of the day, you will get about the same answer, I should say. You'll get 111.62 if you do it this way as well. Now, this one and this number, these two numbers are the same when I rounded to 2 decimal places on my calculator, but when I went out to 5 decimal places, they were a little bit different, and that's because this one integrates, and I have a negative exponent, and when you plug in 2, you get something close to 0. So we get negative exponents with something close to 0, and that kind of makes the numerical algorithm run a little bit longer. And then also it makes that numerical algorithm give you an approximate answer instead of closer to the exact answer. I think this one is easier because it doesn't force me to solve for x, and it's easier to take a derivative in this case compared to this one. Some people might use this one because they like integrating with respect to y. If I have y as a function of x, I tend to like integrating with respect to x. I want you to try another with this section of curve. So we have the same section of curve, y equals x squared plus 2. We're going to rotate that around the line x equals 6 on the interval from x equals 0 to x equals 2. Find the surface area the easiest way possible. That might mean integrating with respect to y. That might mean integrating with respect to x. Again, if you want to try this out on your own, push pause on the video. In a couple of seconds, I will do it. All right, I don't have to redraw this piece of the curve, but we are rotating around x equals 6. When we do this one, my radius is going to go from that curve at some value over to my radius of 6. Now, if I'm integrating with respect to x, then that is going to be just an arbitrary value between 0 and 2. So we're going to get arbitrary x value if I'm integrating with respect to x. It's acting like the radius of the shell method. And this is obviously 6. Now, be careful with this because when we look at a radius, we tend to want to write a positive radius. I keep saying from an arbitrary x value to 6. When I write that in my formula, I'm going to write that as 6 minus x because the 6 is always going to be bigger than the x values that are between 0 and 2. So I will write the radius as 6 minus x so that it comes out as a positive radius so that I get a positive surface area if I'm integrating with respect to x. We can use a lot of the same things we did in the previous examples. For instance, we know already that the derivative is of x squared plus 2 is 2x. We're rotating around x equals 6, and we're integrating from 0 to 2. So my integration is going to go from 0 to 2. My radius, since my radius is going left to right. It's the same thing as the radius on the shell method. So it's from 6 down to an arbitrary x value. The derivative of my function with respect to x is 2x. And now I am ready to plug that into my calculator and figure out what that is. So plugging that into my calculator, again, make sure you are very cognizant of how the parentheses work. A lot of times people will write 6 minus x times square root and forget the parentheses around the 6 minus x, and that throws the entire calculation off. Once you do this calculation, though, you should get 139.00. So the surface area of this object revolving that curve around the line x equals 6 is right about 139. By the way, this is surface area, so it would be in square units. Area is a square units calculation. This is probably the easier way. You could have, if you'd like, do all of your integration with respect to y, but it gets a lot more complicated. So I would prefer to do my integration with respect to x. And if I do that, then the radius is like the radius of the shell method when we found value. So I know that some people get a little bit, their head spins a little bit when they see using these different radiuses or radii. But I wanted to give you this, which radius to use. Well, if I'm revolving around a vertical line is always going to have x equal to some value, like x equals 5, x equals 6, x equals 0. X equals 0 is the y-axis. If I'm integrating with respect to x, then the radius is going to be just arbitrary x value minus this value of the vertical line. Now, it could be the value of the vertical line minus x. That's why I put a plus or minus in front of this, because sometimes the value is bigger than the x's we use. Sometimes the x's we use are bigger than the value. And so we've seen examples of both cases there. So that's where the plus minus comes from. So it's either x minus the value or the value minus the x, which is what you get when you apply a negative. If we're revolving around a vertical line, that is x equals a value, and I'm integrating with respect to y, then the radius is going to be my function minus that value. My function with respect to y minus the value. So the expression, in other words, minus the value. And again, if the value is bigger than the outputs of this function, then I may have to do value minus function instead. It's flipped if we're using horizontal lines. If we're using horizontal lines, then horizontal lines are always written as y equals some value. And if we want to integrate with x, then the radius is going to be the expression minus the value, or the value minus the expression if the value is bigger. If I want to integrate with respect to y, and I'm revolving around a horizontal line, then my radius is going to be y minus that value, or the value minus the y, depending on which one is bigger. So that's what we get and that's how we end up with what we do. So this is a kind of a quick reference if you need it. If you're getting thrown off by, well, should I use the radius with f of x minus a value or just x minus a value? Ask yourself, are we revolving around a vertical line? Integrating with respect to x, we're going to get x minus a value. Revolving around a horizontal line, integrating with respect to x gives me my expression minus some value. Again, the value here is whatever the numerical value of the vertical line or the horizontal line. Let's do another example with a different function. Let's take y equals sine of x, and we're going to revolve that around the line y equals 3 on the interval from 0 to 2 pi. Try this on your own if you'd like, and then in a couple of seconds, I will try it as well. Here is my y equals sine x curve. It goes from 0, it goes from negative infinity to positive infinity, but the section I'm looking at goes from 0 up to 2 pi. So this section here, we're revolving it around the line y equals 3. That is a horizontal line. If I want to use integrations with respect to x, then it's going to be, since the 3 is above my curve, I'm going to do 3 minus f of x, or 3 minus my function, which is sine of x. So 3 minus the expression, that'll be 3 minus sine of x. And then we'll be good to go. I got to do a few things here. First, I'm going to take the derivative. We've already done this in one of our arc length questions. So we get the derivative of sine is cosine of x. When we go to integrate, I'm going to integrate with respect to x because it's much easier to take the derivative of sine than if I were to redo this. I'd have x equals the arc sine or the inverse sine of y. Taking the derivative of arc sine or inverse sine is messy. Much easier to take the derivative of sine. I'm integrating from 0 to 2 pi. Oops, I thought I had pi in there. My radius, again, 3 was above, so I'm going to take 3 minus my function. My function here is sine of x. So 3 minus sine of x is my radius. Make sure that is entirely in parentheses. And then square root of 1 plus the derivative, like we said, is cosine of x. So 1 plus cosine squared. I'm going to integrate that with respect to x. What I ended up with is approximately 144.02. And that gives me my surface area. So an approximation anyways for my surface area. If you had to do this by hand, it would be a lot tougher. So this is the idea. This is how we find surface area again, in this case, we were using a horizontal line and integrating with respect to x. Therefore, we had my function minus a value, or my value minus my function. And if we had, again, horizontal line integrated with respect to x, we had the function minus a value, or again, the negative of that would be the value minus the function. So we had that. By the way, if you accidentally write sine of x minus 3, that would be okay as well. You would just get the negative of the answer that you're looking for. But there you go. Again, if you forget which radius to use, refer back to this slide here. I want to do one more example in this situation. Now we're going to take y equals sine of x. We're going to rotate that around the line y equals 0 on the interval from 0 to 2 pi. Now on this one, if you get too excited and you don't draw what's going on, then you can say, well, since in the previous example, we did this, now all we're doing is changing y of 3 to a y of 0. We could take, well, instead of that 3, I'll just replace it with a 0. Turns out that if you do that, that would be a mistake. And when you plug this into your calculator, you'll actually get 0. The reason is, and it would have worked the same way if you'd have put sine of x minus 0 inside of your parentheses. Doesn't matter which way you integrate that. The reason for that is that sine of x going from 0 to 2 pi on one portion of 0 to 2 pi, sine is above 0. And on another portion, sine is below 0. So if I did this, I'd be wrong. I'd get that the surface area is 0. And the problem is, when I do it this way, then some of my integration is going to count as a positive, having a positive radius, and other portions of this integration are going to count as having a negative radius. And it turns out, in this case, they cancel each other out. And we can see that we've already graphed y equals sine of x from 0 to 2 pi. We can see that here between 0 and pi, the sine is above the x-axis. So if we're revolving around the x-axis, when I do my integration, the radius, in order for the radius to be positive, I'm going to have to do sine minus 0. Between pi and 2 pi, in order for the radius to be positive, I'm going to have to do 0 minus sine. Again, horizontal line. So that's what we're going to do. So that's what I have to do. Since part of this curve is above the line I'm rotating around, and part of the curve is below, I have to split it into 2 sections and then do each section separately. And then add them together. So let's calculate this the proper way. Now the derivative is still the same. we're still going on the interval from 0 to 2 pi, but now I just break up that into two integrations, one of which is going to, well, from 0 to pi, we saw the sine of x is above the 0. So we get that sine of x minus 0 as my radius. And from pi to 2 pi, then we get it the other way. 0 is above sine. So we go 0 minus sine of x. That's all done with respect to x, integrated with respect to x. And when you do this first one, you'll get the exact same value as when you do this second one. And the value is about, of each individually, is about 14.42. And when I double that, I get about 28 point, well, it's actually 8.5 via rounding. So when I double the number, or excuse me, when I add those two together, individually they round to 0.42, but when you add them together, they will, if you add them and then round, it'll round to 0.85. So that's what you should do. Just if you're trying to get an approximation, now we have 28.85 as the surface area of that figure. Again, that figure was taking sine of x and rotating it around the line y equals 0. So in other words, the x-axis. So that's something to be careful of. If your line does cross through the line, if your curve crosses through the line you're rotating it around, you have to realize that maybe some sections of the curve we have to rewrite so that we have a positive radius on all of these. By the way, in this case, again, here's our sine curve. Rotating that around is going to give you this object here. It looks like two, I don't know, two almost ball shapes in a line. Not quite ball, football type shapes. Sine shapes, I guess. By the way, if I zoomed into these, see if I get it. Yep, there we go. Zoomed into these are hollow. These are not solid objects. So they don't have anything inside of them. They're just, again, think of like balloons or something. But that's what we get. That kind of, those objects there. Obviously, they are the same size. That's why we ended up with the roughly 14.42 as a surface area for each. This section, that was the last example in this section. Obviously, we saw a lot of different techniques to find arc length and surface area in this section.